Hello, welcome to module 2 of lecture 5. In the last module, we looked at time constraint scheduling and optimal algorithms for doing time constraint scheduling. In this lecture, in this module, we will look at heuristic strategies for doing time constraint scheduling. So, just to reiterate, what is the problem of time constraint scheduling? It is the problem of scheduling the operations in an operation constraints graph within a given time bound latency known as lambda using the minimum area. And how do we measure this minimum area? In terms of the resources it uses. Last day we said that each resource type has a cost, which is a measure of the area it takes on the floor of the that it is expected to take on the floor of the chip. And when it is known that what is the area of each type of resource on the floor of the chip, the problem is to minimize the summation over cost of the resource into number of resources. So, we looked at the optimal version of those problems of that problem, and today we will look at heuristic solution strategies. The first heuristic solution strategy is a list based strategy. So, when we talked about list based scheduling in the resource constraint scheduling problem, we said that the basic strategy is this: we progress time step by time step. In each time step, there are a set of ready to schedule operations, and these operations have a defined priority on them, and for each type of resource we schedule the highest priority resources of each type, right. So, this was the basic principle of resource constraint scheduling. So, the same principle will be followed here. However, there the priority function for resource constraint scheduling was that it was the weight of the longest path of the critical path from a given node to the sink node. Now, here, because it was a resource constraint scheduling problem, we had to minimize time given a bound on resources. Now, here the priority function will be slightly different. Priority function here is defined by the computation slack available to a node with respect to the latest valid start time that it has. So, how do we find the latest valid start times? We find the latest valid start time using the elapsed scheduling methodology. So, given the elapsed scheduling methodology and the current given the time step given by the elapsed scheduling methodology and the current time step, we can find the computation slack as the difference of the elapsed time minus the current time step. Now, so how does this list scheduling algorithm proceed? Firstly, for each type of resources, we assume that we have only one unit of that resource available. So, we want to minimize resource usage. We only have one unit of that resource available. Now, we do the elapsed schedule to generate the TIL values given latency constraint lambda. Here, we are given a latency constraint bound lambda, and we find the elapsed schedule based on that. Now, obviously, if the elapsed time, that is the latest time that it can be scheduled in, that the first node of the operation constraints graph may be scheduled in is less than 0, then no solution exists. How can this be less than 0? The latency bound is so constrained that even if we have infinite resources, even if we give infinite resources, we cannot schedule the critical path in time, and hence the start time of the first node is less than 0. In that case, no solution obviously exists. Otherwise, again as we said, the scheduling progresses time step by time step. So, L equals to 1 the first time step, and similar to the previous list scheduling algorithm, the algorithm proceeds for each resource type. For each resource type, k equals to 1 to dot dot up to n. Similarly, we determine the candidate operations which means the ready operations that are available at this time step, and then for each of these unscheduled and ready operations at this time step, we calculate SI. What does SI give me? SI gives me the slack, that is what we were looking at, TIL minus L. This is the slack at this point in time. And then what we do? We schedule candidate operations with 0 slack. So, somebody whose slack has reached 0, they must be scheduled. For that, if we need extra resources, we have to give extra resources, because if we do not schedule these operations at that time step, then what will happen? Then we cannot meet the time bound, we will miss the deadline. And then if we then based on after the 0 slack, we have found the operations with 0 slack, and we find whatever number of resources that is required at the time step. Based on that, we update AK. So, AK is the number of resources of type K, and we are handling resources of type K in this iteration. After that, if we have operations left, so when we have updated AK, for all subsequent time steps, the minimum number of resources available to me is AK, right. So, after we have scheduled the 0 slack operations, and let us say not more than AK resources, that means less than AK resources have been required for that, and we have some residual resources that can schedule more operations, we can use this residual remaining resources, because anyway we are not enhancing the number of resources required in the schedule. So, if we have such remaining resources, then schedule candidate operations requiring no additional resources. After doing this, we increment time and we repeat until the schedule is done. So, again, what are we seeing here? For each resource type, k equals to 1, 2 dot dot up to n, we will take the first resource type. We determine the candidate operations for this resource type that are unscheduled and ready. For these unscheduled and ready operations, we find out the maximum slack. What is slack? Slack is a measure of the urgency of this operation at this current in time. Who are the highest urgent operations at any given time? Those with the least slacks. So, if there are candidate operations with slack 0, they must be scheduled at that time step, otherwise the deadline will be missed. If we have such operations, then we update, then we schedule all those operations at that time step. Now, if there is a current value of AK that we are having right now, if the number of operations with 0 slack are more than AK, that means these operations which I must schedule at this time step will require more than the number of resources that I have already allocated. I have to increase the number of resources that I have. So, we have to update AK, we have to increase AK. AK starts with 1 and depending on the number of operations that I have to schedule at a time step, AK increases. Now, however, at all steps we will not have that many operations as AK. Suppose in a prior time step we had many operations with 0 slack, and hence we had to increment AK. But in the next subsequent time step, there are not that many operations with slack 0. So, the number of operations with slack 0 is lower than what was required in a prior time step. So, therefore, the value of AK will be higher than the number of operations with 0 slack. Now, we first allocate all these 0 slack operations onto the resources, but I will have a set of remaining resources at this time step. These resources can be allocated now to other operations with slack higher than 0. So, schedule operations requiring no additional time steps. Obviously, we will start, they will not be 0, but we will be scheduling operations with the lowest available positive slack on these resources. Now, when we have scheduled all the resources, scheduled operations on all the resources at this current time step, we increment time. We increment time, and again a set of operations become available to me, unscheduled another set of unscheduled operations become available to me, and we again compute the slacks, because the slacks may have varied. Suppose I have a set of unscheduled operations that have not actually allocated in the current time step. For all those operations, the slacks in the next time step will reduce, because the value of L has increased. So, T I L minus L will, T I capital L minus L will decrease. So, we have to recompute slacks. Again we schedule operations with 0 slack and update AK, and then again schedule operations requiring no additional slack. This continues until all operations have been scheduled in the graph. So, this is the list scheduling based heuristic strategy for time constraint scheduling. With this, we come to the end of module 2 of lecture 5.